Welcome to another edition of Ordinary Differential Equations. Today we are going to look at some advanced problems related to inverse Laplace transform. Let's go and see what this is about. So we have looked at inverse Laplace transform in some simple problems. What we want to do is to take a look at the tools that are at our disposal to solve problems that start with the following: that we want to find inverse Laplace transform of some function. How do we do this? Let's start by an example. Suppose I want to find inverse Laplace of, say, 5s plus 5 over s squared plus 8s, say, plus 25. This is an important example because it relates to the simple pet functions we had looked at before, the exponential, sine and cosine and so on. Let me remind you of some formulas that we had. We had said Laplace transform of cosine of, say, bt was s over s squared plus b squared. We also did the sine for sine of bt. That becomes b over s squared plus b squared. Then we said if you multiply by an exponential, like exponential of at cosine of bt, what it does is that this exponential creates a shift in your formula, so it becomes s minus a over s minus a squared plus b squared. And similarly, we said if you have exponential times sine, well, it translates the s in this formula, so it becomes b over s minus a squared plus b squared. So you remember we had this type of in this all important table we had a whole pile of these, and you see the hyperbolic trig functions and circular trig functions and their product with the exponential on what it does to the formula in each case. Now the question is, how do we go in reverse? This type of problems, as you might suspect, connect to these, and we need to learn how to take this, decode it so it looks like a combination of these, and then we'll be all done. Two simple steps will do the job. We see that to recognize these things in our table, we need the denominator to be sum or difference of squares. So we need to practice that all important thing from high school, completion of squares. So when this is given, you have to transfer it to this type of expression. And then when that is done, we have to take the numerator and split it between these two types. So two-step process. Let's go get started. So suppose I have s squared plus 8s plus 25. You probably remember this thing from your algebra 1. How do you complete the square on this thing? Assuming that we start with 1, which almost always we do. So we take the 8 and divide by 2, we get 4. We take 4 and square it, I get 16, and add and subtract 16 here. So s squared plus 8s plus 16, and then subtract 16. So what does that do for me? Well, this is guaranteed to be a complete square. This is square of what? You just have a half a second to tell me. This is square of, okay, s plus 4 squared. And this one, well, this is a nice example that happens to be 9, which is, well, 3 squared. So what I did is that this denominator, I made it look like the denominators in the formula. Next, I noticed that in these two Laplace transforms, numerator is either this left element of the base or the right element of the base. Okay, this b matches the b squared here, and s minus a matches s minus a squared here. So in general, if I have a numerator here, I have to write it as sum of a few of these and a few of that. So here is the next step of this problem. First, we write this the denominator. We say, okay, this is s plus 4 squared plus 3 squared, meaning a is minus 4 and b is 3. Now I say, well, the numerator, I want it to be a combination of these two. So I have to be some multiple of s plus 4 and some multiple of 3. You probably can guess what multiple it is, but let me just write it out first time around. Let's just do it formally. So I say some multiple of s plus 4 plus some multiple of a 3 should be in the denominator, that together make that 5s plus 5. And then when I know what multiple it is, I can take this fraction and break it up into two formulas like these two. So in the numerator, what should I do? I have 5s plus 5, and then I have here a times s plus 4 plus b times 3. This is a very simple problem. More often than not, you can just talk your way to the answer, but if you want me to do it formally, so you open this thing, becomes as plus 4a plus 3b. So a has to match 5, so we are already done with a. And then 4a plus 3b has to be 5. Well, this means that 3b is going to be 5 minus 4a. 4a is minus 20, so this becomes minus 15, and then therefore my b becomes minus 5. So what we have here is that a turned out to be 5 and b turned out to be minus 3. So let's write it down here. So I have inverse Laplace of 5 times s plus 4 minus 5 times 3 over s plus 4 squared plus 3 squared. Now I'm going to apply linearity and actually break this thing to two fractions. This is the simplest type of fraction decomposition. So 5 times Laplace transfer of inverse Laplace of s plus 4 over s plus 4 squared plus 3 squared. In that 5 I can also factor it out. In this case, by accident, they turn out these are same numbers. Doesn't have to be like that always. So 3 over s plus 4 squared plus 3 squared. So this turned out to be 5. Oh, now we are in a position to say, okay, we can match against our table. If I have s plus 4 over s plus 4 squared plus 3 squared, means I have exponential of this number, opposite sign of this. So I have plus 4 here, I have to have minus 4 there, and then cosine of 3t. So I have exponential of minus 4t times cosine of 3t. This one, minus 5 exponential of minus 4t times sine of 3t. Of course, it makes sense to factor and do some further simplification, but for now, this is good enough of an answer. So the main tool, one of the main tools that we have for getting inverse Laplace transform is partial fraction decomposition. And this is a very simple case of it, where we do the completion of squares in the denominator, split the numerator accordingly, and then we are done. Let's do another example of this time a little bit simpler, and let's see if you can figure out the answer in a few seconds. Suppose I want to have inverse Laplace transfer of 7s plus 7 over s squared plus 2s plus 82. Okay, take a minute or so to convert this into a form that's going to help me find out the answer from the table quickly. Okay, so do the completion of squares, and then write the numerator as sum of a product of the bases of denominators. That's the deal. So it shouldn't take you more than a minute. Okay, so what is this? Inverse Laplace of this. You can easily tell s squared plus 2s, that must come from s plus 1 squared. Is that right? So I have to borrow 1 from here to complete that. I have 81 left, which is of course square of 9. Numerator, I want to write it as a sum of a product of this and that. It turns out this is a very simple problem, that this is already a product of this, and there is nothing left for the other one. There is no multiple of a 9, or there is no remaining number here for us to worry about. So I'm already done. So what is the final answer? Again, in a few seconds, you pause this thing and quickly tell me what is the deal. So that 7 is a multiple. The addition here refers to the attenuation. You have to take this thing with the negative sign, exponential of minus t, and this is telling you the frequency or the pseudo frequency. This is going to be, which one is it, sine or cosine? Which one? Well, of course, when you have a s here, that's a cosine deal, so it's cosine of 9t. So in your future classes, you are expected to be that quick with Laplace transform, as opposed to going to look at the table and so on and so forth. Okay, okay, some problems at this stage might ask you to find the Laplace transform of a solution of a differential equation and postpone finding the actual solution to a later section. The problems run something like this. They might tell you solve for capital Y, where little y solves the following equation. So I have a piecewise defined function on the right hand side, and perhaps the first piece is active until 1 second, and the second piece is after 1 second. So we might be asked to solve for, now typically we have been looking to solve these things for just y itself, but in order to cut the problem down to a reasonable size and not get ahead of ourselves, some of the problems in your homework, they might ask you just go halfway and find the Laplace transform of solution, and then going back to the little y, that's going to be a topic of a section that is coming up. So how do we handle this? In this type of problems, as before, you just go ahead and take the Laplace transform. So I have Laplace transform of y double prime plus 9y. Well, some initial condition I forgot to write. They might give us, say, y0 is 5, and say y prime 0 is some number, say 8. So the full initial value problem is given and we want to solve it. Right hand side, let's refer to this thing as f of t. So this is a Laplace transform of whatever the right hand side is. Well, we have linearity, so we have Laplace transform of y double prime plus 9 times Laplace transform of y. Right hand side, we said we take our definition, the definition being integral from 0 to infinity of exponential of minus st f of t dt. We take this integral, break it according to our timeline here. We go to 1 second, and then from 1 second we go to infinity. So we go from 0 to 1 of exponential of minus st f of t dt, and then a second batch from 1 to infinity, so we match to the times that we have here, exponential of minus st f of t dt. Why do we do that? It's very simple, because we have a simple formula for each of these pieces, and we can process those integrals straightforward way. Now you remember Laplace transform of a second derivative of a function. This is something that comes up, maybe I should enter it on this table. We did it in was lecture 43. So you remember Laplace transform of f prime, we did that, it's minus f0 times s Laplace transform of f. So that is one simple important formula that we are going to come across many times. And then we have same thing for all derivatives of all orders. We need to have access to all of these things. So for the second derivative, we start with minus f prime 0. So we have Laplace transform of f double prime is minus f prime 0 minus s f0 plus s2 times Laplace transform of f. So we did that in a previous lecture. Maybe it would be best if I put all of them under one single roof so that we refer to them collectively all at the same time. So let me add these two formulas. So for formula number 8, formula number 9, we had for f prime minus f of 0, that's the initial condition, typically refers to position, and then sf, and f double prime start with the initial condition for velocity minus s times initial condition for position plus s squared times the Laplace transform of the function itself. So these two are going to be with us throughout the rest of the semester. We are going to see them over and over again. So you want to find a way of memorizing it and quickly referring to it. So Laplace transform of y double prime, we said it's minus y prime 0 minus s y0 plus s squared times Laplace transform of the function itself y. This is for that first piece. Second piece, 9 times Laplace transform of y. That was, we said, minus y0 plus s times Laplace transform of the function itself, which is now just capital Y. On the right hand side, we have 0 to 1 of f of t at the beginning is just t, exponential of minus st dt. And second piece becomes easier, it's just 1, from 1 to infinity, and that is 1 times exponential of minus st dt. A little bit long in the tooth, but we can manage. So y prime, we said this is 8, this one is 5, and then again this one is 5. For the others, we have to figure out those integrals as well, and perhaps you want to have some of these kind of integrals in some separate table for yourself so that you can do the operation quickly. So what we have here is let's rewrite this thing. This became s squared y minus 5y0 minus s times y0, so that's minus 5s. My handwriting becoming dangerous here because 5 and s looks like each other, and y prime was 8. Here we have s times y minus y0 in this problem okay, sorry, I made a mistake. This is y, it's not y prime, so I have a mistake here. Sorry for that. I have to go and correct this big mistake here. This confused it with, so all I have here is just the y, and so all I have here is just y. I somehow took this thing to be y prime, or kind of two automatics. From y double prime we are skipping the middle term, going to 9y, and so there is nothing there. On the right hand side I have to do two integrals. Let me see if I can convince you to do it quickly. The easy one is this. So integral from 1 to infinity of exponential of minus st. Well, that's going to be exponential of minus st over minus s between 1 and infinity. So that becomes exponential of minus s times infinity minus exponential of minus s times 1 over minus s. For s positive, this is going to become 0 minus exponential of minus s over minus s, which cleans up as such. So that is for that piece. For this piece, how do we do this one? So I have to do integral from 0 to 1 of t exponential of minus st dt. Again, expressions like this show up often enough for you to allocate a page of your notebook for the integrals, so indefinite integrals, and then if the times change, you just adjust accordingly. So what do we do here? We had done this problem before. If you want to refer to that, or if you want to start from scratch, you integration by parts. So u is equal to t, dv is equal to exponential of minus st dt. So du is dt, and v is exponential of minus st over minus s. So that integral becomes uv, which is t exponential of minus st over minus s, and then minus v du, which is exponential of minus st over minus s dt. One more round of simplification, becomes t exponential of minus st over minus s. The two minuses become plus, and then I have to integrate this thing again. It gives me another minus, divide by s again, so it becomes s squared. And now I have to do all of this thing from 0 to 1, because my first integral was from 0 to 1. So at 1 I get exponential of minus s over minus s minus exponential of minus s over s squared. At 0 this becomes 0 this becomes minus 1 over s squared, which when I subtract becomes plus 1 over s squared. Okay, so let's collect everything. This is one piece of the puzzle, that's another piece of the puzzle. So when I write this one, I'll have exponential of minus s over minus s minus exponential of minus s over s squared plus 1 over s squared, and then we have again this one, exponential of minus s over s. As you can notice, these two cancel out. On the left hand side, we go ahead collect our y's, so it becomes s squared plus 9 times y. Everything else we can take to the right hand side, so 5s plus 8 comes here, and these two also are here, so I have minus exponential of minus s over s squared and then 1 over s squared. Rather messy looking expression. So when I want to catch y, I have to take this thing and divide by the coefficient of y, so I'll have 5s plus 8 over s squared plus 9. From these two, perhaps I factor an s squared, they have a common denominator of s squared. I'm also dividing by s squared plus 9. On the numerator, I have 1 minus this, so that becomes our answer. Now perhaps you appreciate why the problem doesn't ask for little y, because then that's going to be an additional layer to this. Notice the solution looks rather complicated, and going back to a table to figure out what the little y is going to require one additional formula which we haven't done yet, but we are going to cover step functions, and that's going to make this problem be doable. Okay, so that was another example. Notice that we let's go back and see what happened. So in the first example, we said we come across this kind of expressions very often because these are exactly the pet functions that relate to oscillations. So main strategy was to complete the square and take the numerator and split it according to the basis of the denominator. Once we have that, we can separate sine and cosine, and then we are all done. Then sometimes we get lucky and the problem doesn't have two pieces, it's just one piece, either just all sine or either all cosine. So well, that's a lucky day and our problem finishes up quickly. Some problems with the complicated right hand side, which is the official term for it is a discontinuous forcing function. So this is like a force that grows linearly with t. Let's just give a little bit of a preview of what's coming up later on. So you have some force that grows up linearly up to some level, and then when it reaches some high value, just stays at that. Okay, so like you say, you ramp up to a certain voltage and then you maintain that voltage or something like that, and then you want to find a response to some stimulus like this. So left hand side, we take the Laplace transform. We had to remember the Laplace transform of derivatives and borrow the formulas from there and bring it here and include it on the left hand side. On the right hand side, I have to take a integral, and that integral has to be done into pieces. Advice here was to make some tables that so that you can do this kind of problems quickly on exams. And we put the pieces together, and well, it doesn't have to look pretty. It as you have more pieces on the right hand side, the capital Y increases in length, and then later on we are going to find out that little y also going to be complicated, and you probably need a graphing software to see what kind of a response do you get. Okay, that is enough for today, and hope to see you in the next class. Until then, good luck and God bless.